So, we will today start discussing our first example problem, and we will learn the use of two things. We will learn the use of what is called a free body diagram, and second we will understand what a rigid body is. Okay. So, let us look at a very simple example. I have a block sitting on an inclined plane. A square block of side 1 meter. A force is exerted on this block at a distance d from the base of the block. We want to find the force required to hold this block in equilibrium. So, a block of mass 10 kg is sitting on an inclined plane of angle 30 degrees. So, this angle here is 30 degrees. If I have a force F being exerted at a distance d, if d equal to half a meter, what is F for equilibrium? Okay. So, we are going to try to go through and understand how to solve this problem. The first concept that we have to understand is what is called a free body diagram. The concept is quite simple. Can I free the body of interest? I will put free in quotes, from all external agents. If I am able to do this, then I can only look at the body of interest. So, in this case the body of interest is this square block. Let us make a list of external agents that I have to free this body of. The first external agent is the inclined plane itself. The second external agent that is going to influence this body is gravity or acceleration that is caused by Earth's attraction of this body. So, if I now I want to replace the act of these two external agents with forces. So, the concept of a free body diagram essentially says I can free the body of all external agents and replace the action of those external agents on this body as forces. And the moment I do that, I can apply Newton's laws of motion to this body alone without needing to consider other external agents such as the inclined plane itself. All right. So, let us go through and draw the free body diagram. I am going to mark the center of mass. Let me magnify this slightly, so I can indicate what I need to indicate. There is the first action is that of the inclined plane. And what does the inclined plane do? If I take the body out, what the inclined plane was doing to this body is essentially exerting a force underneath here. I do not know how it was exerting a force, but there was kind of a force that was being exerted by the inclined plane on this body. So, this is what I will call F1, F1 as I have drawn it is a distribution of forces. There is the force that I need to compute F, and that is acting at distance d equal to half a meter, and the other force I will indicate as F2, which is due to gravity, is going to act vertically, and that is 10 times g newtons. 10 is the mass. So, the force F2 is mg, which is 10 kilograms, multiplied with g, which is 9.8 meters per second squared. So, this comes out to be 98 newtons. So, I will replace this with a number that I have just computed, 98 newtons. The block is 1 meter on the side, like we said, it is a square block, which means the position of the center of mass above is half a meter, and it is also half a meter from the left edge. So, for a uniform block, the forces are, the center of mass is located at the geometric centroid of this square, which is half a meter from each of the sides. If I now take the sum of forces acting on this to be 0. So, what I require for equilibrium sum of all forces, vector sum of all forces is equal to 0, at least that is the first condition. And the second condition is that the summation of all the moments about g is equal to 0. So, let us compute the summation of all the forces, but before I can compute the summation of all the forces, F has a unique line of action, F2 has a unique line of action, but F1 is a bit tricky. F1 does not have a unique line of action, which also means that I need to compute the moment of a distributed force. So, this is kind of a distributed force, but what I can do is I can replace this with a force that acts at a single point on the bottom of this block as an effective force, and let us say that acts at a distance x to the right of the center of mass g. So, the first model that I have introduced is that I have taken what is actually a distributed force underneath the block, the true F1, and replaced it with a point force, with a single force that acts through a point on the bottom of the block as the effective or the resultant force of the set of forces acting on the bottom side. So, let us see if we are now ready to apply our laws of equilibrium. What we find is, now let us take the summation over all the forces F I equal to 0. I can split this into two components, that summation, a vector sum of all the x components of the forces is 0, and the summation of all the y components of the forces is 0. So, for the sake of convenience, I am going to define x as being along the inclined plane and y as being perpendicular to the inclined plane. So, if you notice, I did not define my coordinate system first. I am defining it at a point where I have to do the force computation, because I can look at the forces after I have drawn the free body diagram and choose a coordinate system that would require me to resolve the least number of forces along as components. Say for example, if I choose this x and y as I have drawn here, the force F1 indicated in red here is along the y direction, positive y direction as a matter of fact. The force F is along the negative x direction. So, they each do not contribute either a y or an x component respectively. It is only the weight F2 that I have to now resolve into its components in the x and y direction. And in order to do that, if in this triangle this angle here is 30 degrees, which means this is 60 and this is also 60 degrees, which puts this at 30 degrees, which puts this at 60 degrees. So, if I now take the summation of all the forces acting on this body in the x direction, I am going to take downward positive. I am going to write this as my sign convention all the time, summation x equal to 0. Now, I am adding only the scalar components. This implies minus f plus f2 cosine 60 degrees equal to 0. And if I take the forces in the positive direction of y being positive. So, this symbol here indicates, this convention here indicates is my sign convention. This implies that F1 is in the positive y direction minus F2 sin 60 equal to 0. So, let us go through complete this. So, the first part says minus f plus f2 has a magnitude of 98 newtons, cosine of 60 degrees is 1/2 equal to 0, and f1 minus f2 sin 60 equal to 0. This implies f1 is a force that I do not know the magnitude of, minus 98 times sin 60 is root 3 over 2 equal to 0. So, from the first equation I know that F equal to 49 newtons and F1 equal to 49 times square root of 3 newtons. Now, I have not yet completed the problem, because for equilibrium I have the second condition, that the moments have to all add up to 0. Now, how would I determine that? If d is half a meter, I want to find this effective line of action x shown here. The effective line of action is displaced from the center of mass to accommodate the fact that the sum of the moments have to add up to 0. So, let us now apply that last condition, that summation due to all the forces about g equal to 0, in which implies F1 d1 plus F times d plus F2 times d 2 equal to 0. This is in a slightly generalized way. I am going to use the specific notation. Now, I am going to take clockwise positive, this is my sign convention. If I choose, and it does not matter what sign convention you use, as long as you remain consistent. So, right now I am going to assume that all clockwise moments are positive. Now, the moment due to F1, at least the way I have drawn in this free body diagram, F1 is to the right of G, which means it is going to produce a counterclockwise moment. So, let us say F1 times x with a negative sign, because x positive means counterclockwise, plus F has been determined to be 49 newtons. Now, this d is essentially the distance of the perpendicular distance of the line of action from G. It is not the d that we have shown in the figure. So, let us just to avoid confusion, we will replace this with a new symbol y. Y for this particular instance is 0, because the force F passes through the line of action, because the force is half a meter, which implies y, which is the distance of the force to the line of action itself, is 0, plus F2, which is the weight of the body, which is 98 newtons, also passes through the center of mass. Therefore, the perpendicular distance to its line of action is also 0. So, for equilibrium we require that F1 times x with a negative sign plus 49 times 0 plus 98 times 0 equal to 0. F1 we just found is a non-negative number or a non-zero number, which implies x equal to 0. Okay. So, we have now determined this unknown quantity x, the unknown quantity F1 from and as well as the unknown force F required to hold this body in equilibrium. So, let us draw a free body diagram of this square block once more. With the correct magnitudes of the various forces. So, these are the three forces acting on this body. They are all passing, the lines of action of the three forces are all passing through the center of mass G, which means neither of the three forces is causing a moment about G. So, essentially this system is in equilibrium if the forces are of these magnitudes. Now, in this process we identified or calculated two forces. Okay, let us differentiate between those two. We calculated the magnitudes of both F and F1. So, this is F and this is F1. The difference between, let us understand the difference between F and F1. What causes F1? F1 is a force that is caused by the fact that I have an inclined plane underneath this block. Now, why would the inclined plane push this block up with a force F1? acting through the center of mass in this particular instance? It simply comes from the fact that the inclined plane is rigid, the block is also rigid, and that if I place this block on top of an inclined plane, the block does not penetrate into the inclined plane, neither does the inclined plane push the block by itself. So, the force F1 is actually being generated, is self generated from the constraint that the block cannot go into the inclined plane and neither can the inclined plane naturally push the block above it, and that they would two remain in contact. So, it is essentially a force arising at the contact due to the constraint of no penetration. So, this constraint originated force F1 masquerades as an unknown quantity in our free body diagram because of the fact that we freed the body of the inclined plane as an agent. The moment you free the body of the inclined plane, I have to account for the fact that this body was not allowed to fall into the inclined plane, and that is replaced by an effective force F1 acting perpendicular to the point of contact, perpendicular at the point of contact. So, F1 is a force that originates out of this constraint, as opposed to that F is the force, is the unknown force we wish to calculate to keep this body in equilibrium. So, how much force do I have to exert to keep this body in equilibrium? A 10 kg mass sitting on a 30-degree inclined plane has to have a force of 49 newtons pushing it through the center of mass to keep the body in equilibrium, and that naturally generates an additional force of 49 times square root 3 newtons acting through the center of mass as a result of the inclined plane pushing the block. So, these two forces are fundamentally different. One is caused by the constraint itself, the F1 force. F is the force that we control, F is the force that we wish to control to keep the body in equilibrium. So, we learned the idea of a free body diagram today, and on top of that we learned the application of the two laws of equilibrium for finite sized bodies, the fact that the forces have to add up to 0 and the moments about the center of mass also have to add up to 0. In addition, we learned the fact that forces can come from two different agents, two different kinds of physical processes, one an external agent pushing it and the second from a constraint. Okay. So, we will continue this discussion with another example problem in the next class.